How's it going, guys? Today we're going to go over section 1.2, combining functions, shifting and scaling graphs. So when we combine functions, we do them in two different ways. We can combine functions using just regular operations like addition, subtraction, multiplication, division, and we can also combine functions called composite functions, where we basically take one function and plug it into the other function. So let's start with just the typical addition, subtraction, multiplication, division. So sums, differences, products, and quotients of functions. Like numbers, functions can be added, subtracted, multiplied, and divided, except when the denominator is 0 to produce a new function. So this next part just details that if f and g are functions, then for every x that belongs to the domain of both f and g, that is, for every x as an element of the domain of the function f, intersect the domain of the function g, we define f plus g addition, f minus g subtraction, and fg multiplication by these formulas. So that was a long definition to just describe that if you add one function with another function, you just take whatever that function is and add it straight away with that other function. An example of this would be if my function is x and my other function is 1 plus x. When I add them together, so they would call that f plus g. So if I do f plus g, and they would call that f plus g of x, that would be 1 plus 2x. Or if we'd have written this out to begin with, 1 plus x, so 1 plus 2x, because x and x combine together to be 2x. And then you've got f minus g, you subtract them, and f times g, you multiply them. So then we look at the definition of division. Again, all they're going to say in this is that they define division to be if you have f over g, that means take the function of f and divide it by the function of g. And it says where g of x cannot equal 0. So they're just stating that g of x could not be literally equal to 0. So you couldn't have g of x a function like this. That would be no good. We can't do that. So we would need to have like something like f of x equals 2x, and we could have g of x equal 10, and that would equal, so then you'd have f over g of x would equal 2x over 10. You could simplify that to be x over 5. So that should make some sense to you, what you can do with the addition, subtraction, multiplication, divisions. Let's take a look at this example here. In the example, they have the two functions. You've got f of x is the square root of x. You've got g of x, which is the square root of 1 minus x. The square root of x, the domain, is obviously 0 to infinity because you can't have anything negative. And the domain for g of x is going to be negative infinity to 1. So what they say is the points common to these domains are the points that intersect between them. So 0 to infinity intersect negative infinity to 1. The only thing they have in common are 0 to 1. So the numbers between 0 and 1. So the following table summarizes the formulas and domains for the various algebraic combinations of the two functions. It says we also write f times g for the product function fg. So let's take a look. If we have f plus g, what we do is we take square root of x plus square root 1 minus x. You can see that's pretty straightforward. You just take this here, add it with that. Not a big deal. They say that when you add those together, the domain then for that function is 0 to 1. That's because 1 minus x, its domain is negative infinity to 1. So it cannot have any, for this function here, you cannot plug in anything that's above 1. whereas square root of x has a domain of 0 to infinity. So you cannot plug anything in less than 0. So that means that you, like for this domain here, you can't plug any negatives into this other domain, which is the square root of x, and vice versa. So what that means is the domain, when you combine these two functions together, is simply going to be the numbers between 0 and 1. That's the only thing you can do. When we look at f minus g, that's the same thing. The only difference is they subtract these, but still the domain is the same because this function only basically has negatives up to whole number 1. And this function has 0 all the way to infinity. So if you plug in like -10, it might work for this, but it's not going to work for this function. So the only numbers you can plug in are 0 to 1. And then g minus f is obviously just the opposite. F times g, you're just going to multiply them together. So anytime you multiply square root x times square root 1 minus x, you just take the middles and multiply them and put them under the same fractional sign. If you divide the two functions, again, it's the same. You put them under the functional sign. Instead of multiplying, you're just dividing them. So you have x over 1 minus x, and then vice versa, you have 1 minus x over x. Now, they're going to exclude certain things here from the domain on the division ones because you cannot have 0 in the denominator. So that's why 1 is excluded in this one, because 1 minus 1 would give you 0. And then down here, you're going to exclude 0 because x is in the denominator, and the only thing that you can't plug in there is 0. So it says 0 to 1, and we have to exclude that x cannot be 0. So let's do some examples ourselves. So I just got this straight off the homework. So this should be good because you can see what a homework problem would look like. So find the domain of f. So f is square root x plus 8. So when we look at the domain of f, I always look, okay, I know I can't have a negative number. So what in here will give me the number 0? Well, -8. So -8 is the smallest number I can have. I can plug in -7, -6, 0, 1, 2, 3, anything like that. So -8 to infinity is the domain. And I better put a bracket and a parenthesis. Find the range of f. The range of f then would be all the numbers that it could possibly equal. Well, we know with any square root, 0 to infinity is the most that we can do here. So 0 to infinity, that is the range. That's what the values of any square root. That's what you can get, 0 to infinity, basically every time. G, we have x minus 7. So 7 is going to be a number that we can use. 8's a number we can use. 9's a number we can use. 10's a number we can use. 11, 12, 13, so on and so forth. So 7 to infinity is our domain. For this one, our range is still 0 to infinity. Now if we combine f plus g. So now we're going to combine the two domains. So f plus g, we want to know what, if we go -8 to infinity intersect 7 to infinity. We want to know what that is. Well, what do they have in common? Well, this one doesn't have anything below 7. So any of the numbers like -8, -7, -6 aren't going to work. So really the only numbers that will work are the ones that are in this domain. So really the domain, when we combine these two functions together, is going to have to be 7 to infinity. So 7 to infinity is the domain for that function. So then we have to figure out what the range of that function would be. So the range of the function, well, if 7 is the smallest domain number that I can have, I plug in 7 here. So let's kind of put this down. I'll put it in here. So I put 7 in. So I have square root of 7 plus 8. And then I'm going to be adding that because of the plus function here. And I'm going to get the square root of 7 minus 7. This will give me 0. This gives me square root of 15. So square root of 15, when you add that with 0, is just the square root of 15. So the smallest possible number for our range is going to be square root of 15. well, that's got to be inclusive. And then obviously the biggest, that's just going to continue to go up. So I use 8 here. I mean, this is just going to continue to get bigger. So it's square root of 15 all the way to infinity. And then I look at f times g. So f times g means that what I'm going to do is I'm going to end up with f times g. I'm going to end up with square root of x plus 8 and x minus 7. So again, if I plug in negative 8 here, that's going to zero everything out. If I plug in like negative 7 here, this is going to give me a negative. So when we're multiplying these, our domain is going to have to be the intersection between them. So the domain's got to be the intersection between. I guess I could use negative 8. I just kind of proved negative 8 because if I use negative 8 in here, negative 8 plus 8 is going to give you 0, and 0 times anything over here is going to give you 0. So negative 8 does work, but then after that, the only numbers that are going to work are 7 to infinity. So after that, the only numbers that work are 7 to infinity, I believe. We better check this. What if I use negative 9 here? So if I use negative 9, this kind of threw me for a loop here, guys. So if I use negative 9, I'm going to get a negative in here and a negative in here, right? Negative 1 and negative 16. So that's going to work because when they multiply the two negatives, I'll have a positive number. If I have... Oh, I see what this is going to have happen. That's what that we should plug this. We should kind of plug some numbers in. So let's do that real quick. We're going to plug some numbers in. X, Y. So if I plug in negative 9, I'm going to get negative 1 times negative 16, which is going to give me 16, square root 16. Okay, so that's okay. That will work. If I plug in negative 10, that's going to give me negative 2 times negative 17, which is going to be 34, square root of 34. So that works too. So it looks like these negatives are working. Remember I said negative 8. If you plug negative 8 in here, you're going to get 0. So negative 8 in there is going to give you 0. So one of these possible domains is going to be from negative infinity, because you notice all these negatives from negative 8 and then lower are going to work. So negative infinity to negative 8 is going to be our domain. But that's just the first part of it, because I know if I pick negative 7, let's try some x, y values here. If I pick negative 7, negative 7 goes in here, that's going to be a 1 times negative 7 minus 7 is negative 14. That gives me square root of negative 14. I can't have that. So negative 7 is not going to work. What's the next number that's going to work? Well, it's probably going to be 7. So I plug a 7 in here. 7 plus 8 is 15. 7 minus 7 is 0, so times 0, which gives you square root of 0. That's good. If I pick an 8, this will be positive and this will be positive. So anything 7 and above will also work. So I'm going to union that with 7 to infinity. Sorry that took so long. I didn't expect that to happen. So, but that's pretty interesting. You notice how I ran into a problem and then I used T-charts to figure out my problem. That's what you should do anytime you run into a problem like that, anytime you're looking for domains and ranges. So then what's my range value going to be? Well, it looks like I'm covering all numbers because I get to 0. So basically my range value is still going to be the same range value, which is going to be, I get 0 at some point in time, and then I get all these other numbers above 0, so it's going to be 0 to infinity. because of the square root. Everything I'm getting is from 0 all the way through all the positives. So that's the range of f times g. Let's take a look at the next problem. So now we're going to do divisions here. So we have f of x equals 5. Let's see here. F of x equals 5, and g of x is 3x squared plus 1. Find the domain of f. Domain of f is you can plug anything in because there's nothing to plug it into, so that means our domain is going to be negative infinity to infinity. Because there's no x in there, you can plug anything in. The range, though, is only 5. That's what you get every time. No matter what number you get 5. So that's basically a flat line on the graph. G, though, no matter what you plug in here, negative or positive, you're going to get an answer. So this is going to be negative infinity to infinity, but its output value, 0 is the smallest. If you put in -1, it's going to be the same as 1. So you put a 0 in here. 0 squared is 0, times 3 is 0, add 1 is 1. So your range is going to start at 1, and it's going to go all the way to infinity. Because any of the negatives or positives you plug into this will be above the number 1, be positive above the number 1. So then we look at f over g. F over g would look like this. So I'll write these out here. F over g is going to be 3x squared plus, wrong way. F over g is going to be 5 over 3x squared plus 1. And then g over f is going to be 3x squared plus 1 over 5. So let's take a look at what we have going on here. In the denominator, we have x squared. We can plug in. Well, it looks to me like if we plug in 0, we get a 1 in the denominator. If we plug in anything negative, we're never going to get a negative number here because of this squared. So we can never get 0 in the bottom. So that means that this really has negative infinity to infinity for its domain. We can get anything. For its range, though, the value that we'll get if we plug in, so I got to make a t-chart here. So for f over g, I'm going to have a t-chart. And I'm going to plug in, let's plug in let's start with 0. So 0 plugged in will give us 5 over 1, which is just 5. If I plug in a -1, I'm going to get -1 squared times 3, which is 3, plus 1, which is 4, so I'll get 5 over 4. And then I plug in -2. -2 squared is 4. 4 times 3 is 12, plus 1 is 13, so I get 5 over 13. You notice this is getting closer and closer to 0, right? That's going to be the exact same if I do 1 and 2 because each time I square those. So it looks to me like this is going to get slowly approaching 0, and the biggest number that I had here was 5. So it looks like our range value is going to go from 0 to 5. And it won't touch 0, but it will touch 5. So now we got to do g over f. G over f, it looks to me like no matter what you plug in on top, the smallest number, if you plug a 0 in here, that'll cancel this out, and you'll get 1/5. So the smallest number you can get is 1/5. So we'll write that in, 1/5. The biggest number then you can get is if you plug in, let's see, well, we plug in 2, we're going to get a large number 3. So basically it's going to go from 1/5 all the way to infinity as the domain. So then g of f, so then if we go g over f for the range, you know what, guys? I just screwed that up. This should have been the range. I got ahead of myself. This should be the range. So 1/5 Sorry about that. To infinity is the range. Got distracted, I guess. But I can plug anything I want into that equation. So I can plug anything in. So that's going to be still negative infinity to infinity. Does that make sense? So it's a little bit of work to figure these out, especially domain and ranges, but the process to figure them out, I mean, relatively straightforward. And I won't call it easy because, you know, you got to plug numbers in and all that good stuff. But yeah, it's not too bad. It takes a little time. Let's talk about composition of functions. So you guys should remember composition of functions. If f and g are functions, the composite function f of g is called f composed with g, is defined by, you see this here, basically what you do is you take if you're saying f of g, you're taking the function g and you're plugging it in for the f function. An example of this really quick, if I've got f of x as, let's say, x plus 1, and I've got g of x as x plus 2, if I say f of g of x, that means take this function and put it in for x and this function. So what that'll end up being is f of x plus 2, which is going to be x plus 2. Remember, I'm putting that in for x plus 1, which will end up being x plus 3. So basically, you take this, put it in for x, you end up with x plus 3. So that's composition of functions. Now, there's some descriptions down here that I think are important. It says the definition implies the f of g can be formed when the range of g lies in the domain of f. To find f of g of x, first find g of x, and second find f of g of x. So that's just what I showed you right there. But the key here was can be formed when the range of g lies in the domain of f. So what they're saying there is the range of g has to be in the domain of f. If the range of g is not in the domain of f, then you can't do this f of g. For instance, let's say the range values for g included some values that don't work for f. Like if they didn't work for f, then you couldn't plug it in there. So that's the issue, is to make sure that the range values of g are the same as, are included in the domain of f. They kind of talk about this here, where they say x goes into g, which then goes into the function g of x, which then goes into f, which then gives you f of g of x. Here they say x has to be in g, and g of x, so the range value of g of x has to be in f in order for us to have f of g of x. So they're saying the x value has to be in g, and then whatever that function g of x produces, that value has to be a part of the range of f. If it's not a part of the range of f, it can't be done. All right, let's look at some examples. These ones go a little quicker. I like these type of problems. I'm not going to write them all out. I'm just going to kind of talk about them. But it says f of g of 0. So that means take 0, plug it in for g. So 0 squared is 0 minus 6. So I take negative 6 now and I plug it in here. So this is negative 6 plus 7, which is 1. So then I'm going to go, let's do f of g of x. So if it's just f of g of x, this means they're going to take, I'm plugging an x in here, so I just still have the x squared. So I'm taking this, and I'm putting it in for x on this part. So that gives me x squared minus 6 plus 7, which is going to give you x squared plus 1. And then now I have f of negative 3. So I'm taking negative 3 and I'm plugging it into this function f. Negative 3 plus 7 is 4. And then I'm going to put it in to this function again, which is going to be 4 plus 7, which is 11. So You plug -3 into the function, and you got 4. And then you plug it in, and once you got 4, you plug it back in, and you end up with 11. So f of x is just taking this function and plugging it into itself. So I take this, and I plug it back in there. So I'm really doing f of x plus 7, which is x plus 7 plus 7, which is x plus 14. And now let's talk about the g's. G, f of 0. So I take 0, plug it in here, and that's 7. So now I'm going to put in g of 7, and 7 squared is 49. So I end up with 49 minus 6, which is 43. Now I do g f of x. So I take this, and I plug it in for g. So I'm going to say g of x plus 7. And then when I plug that in, I get x plus 7 inside the square minus 6. Now, they might ask you to simplify this in the homework. If they ask you to simplify this, you just write this out and distribute. But I'm not going to do that here because I'm going to save a little time. G of 3, so I'm going to take 3, put it in here. 3 squared is 9. 9 minus 6 is 3, so I'm going to say now g of 3 again. So we just did it. 3 squared minus 6 is, you'll see that here, is going to be 3. And now g of x. So I'm going to take x squared minus 6, put it in for g of x. So I end up with g x squared minus 6. And I put that into its own function, and I get x squared minus 6 squared minus 6. And again, they might ask you to simplify that, but you can see, I know you can do that on your own. So that is composite functions. Now, you'll get lots of practice in the homework on that. And then finally, something that I'm not necessarily as confident in, it's going to require practice on my end and on your end for sure, is this vertical shifts and scaling and stretching and all that good stuff. So basically shifting, so if you want to shift a graph, so it says shifting a graph of a function. A common way to obtain a new function from an existing one is by adding a constant to each output of the existing function or its input variable. The graph of the new function is the graph of the original function shifted vertically or horizontally, as follows. So vertical shifts. Here's the important part. K. So if this is your original function, and then you're going to say plus k, what you're doing is you're adding a number to the range of the function. So you're adding a number to the range. Anytime you add a number to the range, well, the range is always going to be the vertical axis. So the range, remember, the domain is always the x. The range is always the y. So whenever you add a k, because you're adding it to the function, which then affects the range, that's going to be the vertical shift. But if you take the same number and you add it, you're adding to x. So before you actually even put it into the function, you're adding to x. You're adding to the domain. Anytime you add to the domain, that affects the horizontal shift. So if you notice down here, if you take a formula y equals x squared and you add a 1 to the end of it, that's going to be a vertical shift up because you're affecting the y value. So you're adding a value of 1 to the x squared. So what you're getting is a vertical shift, and you can see that right here with this one right here. That's a vertical shift, okay? And that's y equals x squared plus 1. If you look at this one, this is y equals x squared plus 2. They added a 2, so that's a vertical shift of 2. It's the same function, but just 2 higher. And then if you have a minus 2, that's going to go down 2. Okay, so you have a vertical shift down 2. Horizontal shifts then are going to look like this. So if you add a 3 to the domain of the function before you square it, so if you look at this, the original function was y equals x squared. And then I'm adding a 3 to it. So instead of x squared, now I have x plus 3 inside the square. What I'm doing is I'm getting an extra 3 in my domain, so I'm adding 3 to the domain, which means I'm adding 3 to the x-axis. Now, this affects it in the opposite direction. So when you add 3, you're actually shifting it left 3 on the graph. When you subtract 2 from the domain part of it, you're actually moving it to the right. So that's the horizontal shift when you add something to the domain. And then we look at vertical and horizontal scaling reflecting formula. So there's a lot here. So a lot of this you might just need to read a little bit. I'm going to kind of give you the highlights real quick, and then I'm going to have you read and kind of look at the graphs. It's really important for you to look at all these graphs on here. So vertical and horizontal scaling. If I add a number that's above 1, if I multiply a number that's above 1 to the function, it's going to stretch the graph vertically by a factor of that function. If I multiply by a fractional number, which is less than 1, it's going to compress the graph vertically. So that should be simple. You multiply by a number, that kind of makes sense. You multiply by a number that's above 1, it's going to stretch it. If you multiply a number that's below 1, it's going to or between 0 and 1, it's going to compress it. And then you can compress it horizontally. So again, this up here was to the range value. Now this is to the domain. You're multiplying something to the domain value, the x-axis. So when you multiply to the x-axis, it's going to have a reverse effect here. So instead of stretching it like this one up here, it's actually compressing. And then if you were to divide by something inside of the range, it's actually going to stretch it horizontally. So this is what compresses and stretches something horizontally, is by messing with the domain, either multiplying, which would compress it, or dividing, which would stretch it. And then if you want to reflect something, so reflects the graph across the x-axis. If you put a negative on the range, so if you change the range value by throwing a -1 on there, it's going to reflect it across the x-axis, which means it's going to take and reflect it from top to bottom. If you put a negative on the domain part of it, it's going to reflect it now on the y-axis. So it's going to, before it was vertically, right? Again, where it's always vertical if it's on the range value. So it went from the top to the bottom. This one's going to go from across the y-axis. So it's going to go from the either right to the left or the left to the right. They got some examples down here, and you really need to look at these examples. And I'm going to talk through them, but they do a pretty darn good job of explaining it. So it says multiplying the right-hand side of y. So it's all dealing with this function. So that's the big thing, is take a look at that function. It says if you multiply the right-hand side of y by 3, so you'll get 3 square root of x. It says it stretches it. And we know that because of the function we had above. If we're multiplying and we're changing the range value, we're stretching that. They show that right here. So this here is the original value right there. And by multiplying by 3, of course, it's going to stretch this thing out because you're going to get range values that are higher. Now, if you want to compress it, then they multiply it by 1/3. And you can see that here, multiplied by 1/3. Now it compresses it. Boom, it's down here. It's much smaller range values because you just multiplied all the range values by 1/3. And then if you want to look at the horizontal stretching and compressing, you can see that here. So if we want to compress it and stretch it horizontally, this was stretching it up vertically. This will stretch it left and right here. So if you take, and you can see that stretch here. So if you stretch it, if you got the same function and you put a 3 on the inside on the domain, that's going to compress the function. So it compresses it, and it squeezes it this direction toward the y-axis, On this one here, though, by putting a division of 3, it's going to stretch it. So it's going to stretch it out horizontally this direction. So it's like if you took that and you pulled it this direction, that's what this division of 3 does. And if you had the multiplication of 3, it's like taking and pushing it this direction. If you can think of like a piece of wire or something. And then reflections. So you can see here that if you reflect across the x-axis, it's because you're changing the range value. You put a negative here, and that's changing the range value, and it reflects it across the x-axis. It's not showing up very well, but if you had a function that was this direction, up and down like so, and you reflect it across, it would be because of this negative on the domain. So that is the stretching. That's going to take you some time. You need to really look at all these graphs, and then it might take you a few tries on your homework, but eventually by doing quite a few of these problems, you'll get it figured out and it'll make some sense. So that's the lesson.